Hello and welcome to the Covalent Compounds and VSEPR Theory video activity. We should begin by reviewing a touch of what we talked about in the last video. So we talked about the octet rule, where elements can exchange electrons to form ionic compounds, and in this video we'll be dealing primarily with how they can share electrons to form covalent compounds. And so octet rule states again that elements want to generally end up with the same electron arrangement as the nearest noble gas, and this generally means 8 valence electrons. And so our nonmetals right here, initially they each have 7 valence electrons represented by these 7 dots, and if they come together and share, they both get to count the shared electrons, so now each atom has 8 valence electrons. And so this is the reason why these covalent bonds form. Let's talk a little bit about the differences between ionic and covalent compounds. So covalent compounds can be solids, liquids, or gases at room temperature. They tend to have significantly lower melting and boiling points than ionic compounds, and they generally do not conduct electricity when you melt them or dissolve them in water. And so they're made of distinct molecules. The water is made of H2O, carbon dioxide is made of CO2 molecules, and glucose is made from C6H12O6, meaning that each glucose molecule has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Ionic compounds, on the other hand, have very different properties. So these tend to be very hard, brittle, crystalline solids at room temperature, and they have very high melting and boiling points when compared to their covalent cousins. And these ionic compounds, if we melt them or when we dissolve them in water, they end up conducting electricity. And we have some examples right here. Sodium chloride, sodium bicarbonate, which is baking soda, and magnesium hydroxide right here. And so notice that these ionic compounds generally contain metals. So I would like you to pause the video and go ahead and complete question number 1 on the activity. Welcome back. Let's talk a little bit about the process of covalent bond formation. We're going to begin by looking at the simplest possible molecule, which is the H2 molecule. And so what happens is our hydrogen atoms move closer together, and then our electrons end up being shared between these two atoms. And so our electrons spend the majority of their time hanging out between the nuclei, these bonding electrons here. And the attraction between the nuclei and the bonding electrons are actually what tether these two atoms together. That's the attractive force that holds the bond together. Now, if we take a look at a slightly more complex molecule, look at fluorine, each of these fluorine atoms has 7 valence electrons represented by these 7 dots. And they're going to come together and they're going to share electrons. We're going to form a bonding pair, so that's a pair of electrons that's going to be used to bond. And then we have our lone pairs. And so notice the word pairs here. That means that electrons generally like to exist in groups of 2. And so in order to satisfy the octet rule in this case, we not only have our bonding pair, our bond of electrons here, we also have these lone pairs which don't participate in the bonding. So we're not going to deal with the process of drawing these types of dot structures, or Lewis structures as they're known, significantly in this video because we have a lab devoted to that. And so just be aware you'll be exploring how to do this in a lab, but I wanted to introduce you guys to the terms lone pair and bonding pair. So moving on, we can actually use the octet rule to predict how many bonds the different elements are going to form. And so the elements in group 7a, they have 7 valence electrons. They need to form just 1 bond to reach 8 valence electrons. And so these elements are going to, chlorine, fluorine, bromine, iodine, etc., are going to tend to form 1 bond. And they're going to also require 3 lone pairs in order to satisfy the octet rule. The elements in group 6a tend to form 2 bonds because they have 6 valence electrons, they need 2 more, but they also tend to have 2 lone pairs in order to satisfy that octet rule. Over here we have nitrogen and phosphorus in group 5a. They need 3 more valence electrons to satisfy the octet rule, therefore they like to form 3 bonds. And they also need 1 lone pair to reach that total of 8 valence electrons. Group 4a, these elements will consistently form 4 bonds, and they have no lone pairs because those 4 bonds give them all 8 valence electrons. Boron we're not interested in because it's not very prevalent in biochemistry, but hydrogen is an unusual one. We mentioned before it needs only 1 bond and no lone pairs to be satisfied. That's because it's trying to mimic its nearest noble gas, which is helium. It needs just 2 valence electrons, so it forms 1 bond to get that. So I'd like you to pause the video and please complete questions 2 through 4. Let's talk about naming covalent compounds. The good news is they're much simpler to name than the ionic compounds. Like the ionic compounds, the first element in the formula is also the first in the name. The second element in the formula is the second in the name, and we give the second element the "-ide stem in the name. And we use prefixes to indicate the number of atoms, or the subscripts of that formula. So here are our prefixes. We have mono, di, and tri, meaning 1 through 3, tetra, penta, etc., etc. And I should point out that the mono prefix is generally omitted in the name. If there's no prefix, assume that there's one of that particular element. And so on the next page we have a list of some compounds here and their names. So CS2, we call this carbon disulfide, so notice the mono is omitted. The first element in the formula is also first in the name, and the di tells us we have 2 sulfurs. Over here we have sulfur hexafluoride, so we have 1 sulfur and 6 fluorines, and so the mono is omitted for the sulfur. And the hexa tells us there's 6 fluorines, and again notice that we change the suffix here to "-ide", so it goes from fluorine to fluoride, so sulfur hexafluoride. And that's all you need to know for naming these covalent compounds. So I'd like you to pause the video and please complete question number 5 on the activity. Another thing we'll be doing this chapter is learning to predict the shapes of molecules. And in order to predict these shapes, we first have to draw the dot structure or the Lewis structure, 2 different names for the same thing there. And once again, we'll be learning how to do that in a lab, so we're not going to go into that in detail in this video here. But once we look at our dot structure, if we happen to have 2 bonded atoms and 0 lone pairs around our central atom, so again, around our central atom, if there's 2 bonded atoms and 0 lone pairs, our shape is going to be linear. And so we refer to this as 2 electron groups. The electron groups, again, are items around our central atom. If we have 3 bonded atoms and 0 lone pairs around our central atom, this is going to be referred to as trigonoplanar. It's a flat triangle. And if we have 2 bonded atoms and 1 lone pair, this is going to be bent with a 120-degree angle. And there's a picture of it. And so I want to point out, notice it doesn't say bonds here, it says bonded atoms. So even though we have a double bond in this SO2 molecule, it's still just 2 atoms bonded to our central sulfur atom. So 2 bonded atoms, and we can't see in our picture here, but in the dot structure we'd have a lone pair on the sulfur. So 2 bonded atoms, 1 lone pair is always bent. If we have 4 bonded atoms and 0 lone pairs, we're going to have a tetrahedral shape, and there's a diagram of it. So once we get to 4 electron groups, this is where we sort of go into 3 dimensions rather than 2, can spread out these atoms further apart. So VSEPR theory is based on a very simple idea. The theory is based on the idea that these bonds and lone pairs are all made of electrons. Electrons are all negative, and therefore they repel each other. So we want to maximize the distance between them. And spreading to 3 dimensions is how we maximize that distance here. If we have 3 bonded atoms and 1 lone pair, this is going to be trigonal pyramidal. And so it looks like kind of a triangular pyramid. And finally, if we have 2 bonded atoms and 2 lone pairs, we have bent now with a 109-degree angle. And I want to point out that we'll be practicing in the lab drawing 3-dimensional shapes. So don't worry about that for now. We're practicing our techniques for drawing these 3-dimensional shapes, but I want you to be able to identify the shapes based upon the dot structures. So I'd like you to now pause the video and complete the VSEPR table on the activity. So here are some dot structures. Let's figure out these shapes based upon the dot structures and using the table on the previous page. So we have NF3 here. There's our dot structure for it. If we look at our central atom, it has 3 bonded atoms attached to it and 1 lone pair. If we refer back to our chart here, 3 bonded atoms and 1 lone pair is going to be trigonal pyramidal in shape. So this is going to be trigonal pyramidal. And next we're asked, what is the shape of carbon disulfide, CS2? Here's our dot structure for that molecule. And so if we look around our carbon has 0 lone pairs and it has actually 2 bonded atoms. So again, notice the only lone pairs that affect the shape are the ones in the central atom. Although we have lone pairs, we have none on the carbon. And so going back to our trusty chart here, if we have two bonded atoms, 0 lone pairs, our shape's going to be linear, and sure enough, our CS2 molecule is linear. So I'd like you to now pause the video, complete question 6 on the activity, and once you've done that, go ahead and scoot on over into the discussion and post any comments and questions and help out your classmates. Thank you. Bye.